Overload relays, these are an important part of your typical motor control system. They're a bit being overcome by technology in that VFDs don't require them. So once you stick in an electronic motor controller, the electronic motor controller can take care of the overload portion. But we're going to look at some basically the differences between fuses and circuit breakers and the overloads, some different types of overloads, how they're used in a motor control circuit, and we'll take a look at CTs and choosing and setting an overload. So circuit breakers don't protect the motor from an overload. So the circuit breaker is set high so that the motor can start. When a motor starts, there's a lot of current flowing. So we got to install a circuit breaker that's kind of big. Then the overload is set small, but it has a long time delay. So that short duration motor starting doesn't trip the overload. The overload only trips when you have a lot of current. So in this example, we have 15 amps flowing, the motor's overheating, the circuit breaker is not tripping. Hopefully there's an overload in here that will trip. So circuit breakers are short circuit protection. Fuses are normally short circuit protection. They're not overload protection per se for motor circuits. But you can get dual element fuses that provide overload protection. But anyway, so in a motor circuit, our fuses and circuit breakers are typically short circuit or ground fault protection, and typically overload protection is there for the longer, slower problems. And that's usually the problem is usually too much mechanical load attached to the shaft of the motor, which creates too much current flowing. And if that persists for too long, you get heat, and you get too much heat, you damage insulation. Incidentally, all electrical equipment is basically rated on heat, right? The warmer it gets, eventually the insulation dies. So it's all comes back to heat. So heat, essentially, a thermal overload then it's a little unit that's put in series with the motor load, and if it gets warm enough, it trips, or it'll trip a set of contacts is usually the way that works. So there's a couple different types. There's a melting type and there's a bimetal type. Now these are older. If you buy anything new, it'll be electronic. But you'll see them in older setups, and you'll see them in the lab too. So here are these mechanical types. This is the type that basically you got something in a tube that melts, and then it'll get solid after it cools. And then this is the bimetallic strip, and essentially it's two different metals that will expand at a different rate when heated, and so it causes the strip to warp and trip. So thermal overloads are put in every phase. So if you got a three-phase motor, there's one in each of the three phases. So magnetic overload is controlled electronically, and it's, instead of it being heat based, it's based on the strength of the magnetic field. And then you can get these electronic ones that are really, you can get them that are quite fancy, that do a lot. But they all have the same basic principle. They sense the current, and then they'll trip the control circuit. Usually they do not trip the motor circuit directly, only on very small applications. And that's what we saw with the manual motor starter. Very small applications, we will trip the motor directly. So these motor overloads come in classes, and what a class has to do with is the time delay. So if we come out here and look at this 10-second mark and this 20-second mark and the 30-second mark, you'll see that corresponds to 4 times the rating of the device. So if I have a 10 amp overload, then if there's 40 amps flowing through it, it'll take 10 seconds to trip for a class 10, 20 seconds for a class 20, 30 seconds for a class 30. So the 30 is slower than the 10, or sorry, the 10 is, 10 is fast, 30 is slow. Okay, and you notice as you get back here to 1, which would be in that instance 10 amps, right here 10 amps, it basically won't trip, or if it does trip, it's going to take a long time. All right, we set these according to NEC 430.32, 115% or 125%, and that's based on, well, you have to go back and read that, but it's based on the service factor of the motor. So how do these work? Okay, so here's the actual overload in the schematic, this top part being power, the bottom part being control. So this up here might be 480 volts. This down here could be a small voltage, maybe 120 or 24 volts. Here's my control drawing. Here's my power drawing. So in the power circuit are the overload elements, the sensing elements. They do not trip the current. This could be 200 amps. These little tiny overloads do not trip the current. What they do is they cause these little tiny contacts to trip, which kills power to this circuit down here, the control circuit, which kills power to this little coil. And when the coil dies, the contactor opens and boom, power is disconnected from the motor. So overload relays are normally closed in our circuits. See how they got the slash through them? And once these heat up, they become open. All right, they're in series with the motor contact coil. So there's the motor contactor coil. They're also, the sensing elements are in series with the actual motor. Here's another picture of them. Sometimes you don't just have normally closed, but you have some normally open contacts, and you can use those for other things. So in this case, we're turning on a light to alert the operator that there's been a overload trip. Okay, on large motors, we'll use something called a CT, or current transformer, which we'll spend more time with later. And that current transformer will sense current, and we'll use that to and work with that. All right. Now, the way current transformers work, they work based on there's ratio. So a 200 to 5 CT, if you put 200 volts on the primary, you'll get 5 amps on the secondary. If you put 100 volts, you'd get 2.5. But we'll spend more time with those later. I'm going to make a plug for CTs. A safe CT is a shorted CT. Woo! And that's totally opposite from what we're used to with, say, voltage transformers. But for now, you'll have to take my word for it, and we'll play with that later.